Okay. All right. So let's see here. So in order to solve for time or n, we needed to use a logarithm, right? Now the logarithms, they have a lot of useful properties for some equations, right? So properties of logarithms, right? So when we say log of a, right? Yeah, thank you for the reminder, Iglesia, right? By the end of this week, submit any late homework you would like for me to grade. All right, so the logarithms have lots of useful properties. They kind of have their own kind of rules that don't really follow the algebraic rules that we're used to, right? And we could see kind of why they're useful for certain applications, right? Now, if you think A and B, think of them as just two numbers, right? The nice thing about the logarithm is that it changes a product into a sum. And it changes a division into a difference. Right, so lots of interesting properties for a logarithm. Now, in terms for our applications, one that really is going to be very helpful here for us is the one of the exponent, right? And that's the one that we kept referencing over and over, right? If we have a to some power n, then we can take that n, and instead of an exponent, it becomes a coefficient, which is very useful because now it allows me to, if you notice all of those equations, whether it be compound interest, any of the annuity formulas, the time variable is always the exponent. So if I want to solve for it, I'd like to get it out of the exponent. And the way that I'm going to do that is by using a logarithm, right? So this is going to be the property that we will be using, right? So let's kind of see, let's do an example here. All right, so let's say in this example, it says you have managed to save $1 million for retirement, and you plan to withdraw $3,000 a month from an account that earns 2.25%, right? So for how many years will your retirement fund last, right? So again, right, always ask yourself with any of these problems here, right? What am I doing in this situation, right? Am I depositing? And if I am depositing, is it just one deposit, right? Or is it multiple deposits? Or am I withdrawing, right? Or am I making multiple payments, right? So in this case, we see, all right, you plan to withdraw, multiple payments. So I'm withdrawing $3,000 a month, right? So when we see, all right, withdrawals, this is a payout annuity. Yes, these notes have been, and I posted them on Canvas on Monday. Okay. Okay, so now I've identified the formula, right? So that's the first challenge that we need to identify, right? So identify the formula. So let me see here. Let me go off of memory here. I think the payout annuity is D. Withdrawing, so it's 1 minus 1 plus R over K, negative N to the K, all over R over K. All right, I'm pretty sure that's the payout annuity formula. Okay. All right. So that would be the formula that we're using, right? Now let's determine what it is that we know, right? We know the starting balance, right? We know P naught is $1 million. All right, I know the interest rate on this account. The interest rate is 0.0225. D is the monthly withdrawal. In this case, D is going to be 3,000. All right, and then K, we assume the interest compounds. Since we are withdrawing monthly, we'll assume that that is the same at the same rate, the same kind of interval that I get interest, that I earn interest on the account. All right. Okay, so we've identified all the pieces of information, right? And again, as you kind of work through these problems, I'd like to see this from you guys as well, right? Don't just jump and start plugging in numbers into a formula in your calculator. Like, write it out, right? It's easier to kind of troubleshoot in this way. You can kind of go back to your work, right, instead of having everything in your calculator screen. Okay. So let's plug things into our formula here. So we're going to have 1 and then D is 3,000. And then negative 12N. Okay. All right, so now let's start. So we have it all in our formula there. It's supposed to be 0. And now let's go through trying to solve for this formula here, or solve for N in this case, excuse me. So I'm going to start by plugging in my calculator, the denominator there, 0.0225 over 12. So when I do that, we have $1 million. And then here we have 3,000. Okay. All right. Okay, so that is my first step, right? Just doing the R over K calculation, adding it to 1 in the numerator, and just writing whatever I get for R divided by K. All right. So from here, again, right, my goal is to solve for that value of N. So I'm going to go ahead and multiply both sides by the denominator. So I'm going to multiply . And I multiply here by 0.001875. All right, so I'm going to multiply both sides of the equation by the denominator there. And on the left-hand side, we'll get $1 million times 0.001875. And that leaves me with 1875. And on this side, this reduces to 1, right? And we're simply left with 3,000. Negative 12. Okay. All right. And again, it eliminated the fraction. All right. So now again, right, it's getting closer and closer to that N, right? One step at a time, right? We can't just jump to the end, right? The next thing to account for is that 3,000 in front of the parentheses. So what I'm going to do from here is I'm going to divide both sides by 3,000. All right, and we get 1875 divided by 3,000. And we get 0.625. And then here that reduces to 1. And then I can drop that outer parentheses and simply have 1 minus 0, 0. Okay. All right. And again, right, each step of the way, the equation is getting more simplified, right? Getting closer and closer to our goal, which is to to find the value for n. All right. Okay. So the next thing would be, I'm going to subtract 1. So I get 0.625 minus 1, and that gives me negative. Okay, and then before I take the logarithm of both sides, I'm going to multiply both sides of the equation by -1 to get positives here. So here I'll multiply by -1, multiply here by -1, and we get 0.375 is equal to 1.001875 to the -12n. Excuse me. All right. All right, so then from here, now I'm ready to take the logarithm of both sides, right? So now what I'm going to do, and I'm running out of space here, so I'm going to, the best way to create some space here. Okay, that should be enough there. Okay, so from here, I'll take the log of both sides. So we'll take log of 0.375, log Okay, and then here, right, the purpose of this is to use the property of logarithms where I could take the exponent and make that into the coefficient. Okay, and now I can divide both sides here by -12 log 0.001875. Okay, and again, the reason for doing that is we see, all right, that reduces to 1. All right, and that reduces to 1. So on the right side of the equation, I'm left with n. All right, which is what I want, right? I want n equals to something. Now, as far as the left side, let's kind of bring up our calculator here. Okay, and then from here, clear this out here, and let me plug in log of 0.375. And from there, I'm going to divide that by, I'm going to open another set of parentheses and plug down there at the bottom -12 log of 1.375. 0.001875. Okay, and did I plug in negative 12? Yes, okay. Now, it's important here that once you hit, so you write the numerator, log of 0.375. It's important that after you hit divide, you open up that parentheses. Do I need one more? Let's see here. Close it up. Yeah. Okay. All right. So it's important here that when you do this, that you open up that set of parentheses, because again, right, your calculator is very fast. It does calculations incredibly fast. It is not very smart though, right? It needs to be told exactly what to do. If you don't have the parentheses there, it will divide by negative 12, but then it'll multiply the whole thing by the log, which is not what you want, right? You want to make sure that you do negative 12 times the log and then do the division problem, all right? Usually gives an error too. Okay. Okay, so another thing there might give you an error as well. All right, so we hit enter here. Okay, and we get a 43.6 years, we see, since we're dealing in years. Okay, so the $1 million will last you about 43.6 years in an account that earns 2.25% interest, so not bad. So let's say you retire at 60 and you live till you have a $3,000 income till you're about 100 years old. Mm-hmm. Okay. If we need to solve for n, and n is in our exponent, in order to get it out of the exponent, we're going to need a logarithm. So yes, right? So all the problems that are asking for time or how long something lasts are going to involve a logarithm. Well, you might have to move to Idaho. All right. Okay. All right. Any other questions at this point here? All right. Let's do the next one, man. Okay. So let's look at the next example here. Oh, it's still there. Oh. There we go. What do you mean just 43.6 years? That is how long the money will last, correct? Yes, that is the solution for n, right? All right, so let's see. Let's take a look at this next one here. If you invest $2,000 at 6% compounded monthly, how long will it take the account to double in value? Okay, so again, one of those how long it will take for something to happen, right? So it looks like we're going to be solving for n, so we're going to be needing a logarithm to do this. All right, so let's see here. If you invest 2,000, now which formula am I using here? All right, let's try to, again, first step, right? Always identify what is the formula that we're using. Now, based on just kind of the the context clues here. It looks like I make one initial deposit of $2,000, right? It just says you invest $2,000. There's no quantifiers, there's no a month, it just says 2,000. Okay, so that's telling me, all right, that's a one-time deposit. And thinking of that, it doesn't say there's any additional withdrawals. So if I'm just making a one-time deposit here, all right, what formula is the one that I use for one lump sum deposit? You guys remember? Yeah, this one is the compound interest one, right? That's accounts for when you make a deposit and then you forget about it, right? You don't withdraw or you don't add to it. So this one is going to be the compound interest formula. Here. NK. I believe that's it. Going off the top of my head here. Yeah, it should be plus. Okay. Yeah, that's it. All right. They're all the same. They're all the same problem, right? Again, it's just a story that you have to identify. Excuse me. Okay, now P0 is the initial amount, and Pn is the amount after however many years. So I know my initial is $2,000. Right? What is Pn going to be? What am I waiting for my money to do in this account? We're not solving for A, we're solving for N. I need to know Pn, right? And in fact, it's telling me Pn. I just have to decipher it, right? How long till what? What is it asking for? How long till what happens? So you look here. How long will it take the account to double in value, right? So that means that Pn until it doubles, and that is $4,000, right? Okay. Yes, double in value, but if we know the initial, then double means just times 2, right? So if the initial is 2,000, to double means the account has a value of $4,000. Okay. Double. All right, so here we have, if you invest $2,000 at 6% compounded monthly, so R is 6%, K is 12, right? Monthly compound interest. Okay, so now we have everything we need here. Pn is 4,000. Okay, so I'll plug things in. And again, let me start by, this one is less kind of complicated than the annuity ones, right? It's more straightforward. So I'm gonna start by, inside the parentheses, calculating what that value is. So 1 plus 0.06 over 12, and we get 12, and yes, thank you. All right. Okay, so we do that. And then the next step is let me divide by 2,000 on both sides. All right, and then that reduces to 1. And then on the left side, 4,000 divided by 2,000 is 2. Right, and then over here we'll have 1.005. Okay, and now I have what I have the n that I want to solve in the exponent, and at this step is where I'll take the natural or the logarithm of both sides here. All right. And now I'll use that property of logarithms where I can write the exponent as a coefficient. All right, and this last step, to solve for n, I'll divide both sides by 12 log 1.005. All right, and notice here the 12 reduces to 1, and then log reduces to 1 as well. Okay, so on the right side of the equation, we'll have n, and on the left, let me bring back the calculator here. Okay, so we'll have log of 2 and divide, open again, don't forget open that set of parentheses, 12 log of 1.005, and then close your parentheses. Okay, and then we hit enter. And we get, it'll take about 11.6 years, so a little bit over 11.5 years. So let's go back here to our notes. To double. Okay. All right. Any questions on this example here? Okay, now let's say that I started with $10,000 and I wanted to figure out how long will it take my money to double from $10,000. Would that change my answer for this problem? What do you guys think? All right, so let's say that instead, let me write this here. We start with $10,000 and you want to get to $20,000, or in other words, double, right? With the same other parameters, right? 6% interest, monthly, right? Correct, Archie, it would not change, right? The doubling time is independent. It's a good thing to kind of realize here. The initial amount that you start with, it could have been $1, right? In order for that $1 to double, it'll still take 11.6 years, all right? So in this type of problem, we're asking about doubling, right? The initial amount really is unimportant, because if you notice here, if you look at the equation here where you when we account for money, right, that division comes along here, and when you do that, this ratio of doubling will always get you 2. So the initial amount that you start with really is not important, right? In terms of, if we just think of relative terms, right? I want to find out when it doubles or when it triples or whatever, right? that initial amount is essentially irrelevant. You can just ask how long would it take your money to double, right? The amount really here you could be is really flexible, right? So it still takes 11.6 years. All right. The only difference here, all right, you can plug in your answer up here for n, and if you plug in, you can always, this is an equation, right? So if you plug in the values here on the right and the left side of the equation, you should get the same result. All right. All right. Okay, any questions on this example? All right, just based off of our time here, I'm gonna skip the last one here. Again, it's just more of solving for n, and I am gonna address some of your questions for the project. Let me pull the project up. I have it here. I do not, okay. All right, here, so.